Welcome to this Java Break with Basis. Today is the third of our three-part series on BBJ12. In this final part, we'll show you how the best BBX has just got faster. My name is Nick Spence. I'm the Chairman and CEO of Basis International. I'm very excited to take you through today's agenda. We're going to show you how BBJ's language has been optimized to be faster. We'll tell you about how Java 1.7 is faster than 1.6. 1.7 is fully supported with BBJ12. We'll show you how Barista has been optimized to execute faster. We'll finish off with a review of development tools. We'll show you how custom development can be faster with the Dialog Wizard. And we'll show you how creating documentation is faster. And then we'll take your questions. So hold on to your seats as we zip through this presentation. Sorry about that, couldn't resist the temptation to go even faster. Well, let's talk about the fastest BBJ by far. String handling has been refactored. Most of our application programs make heavy use of strings. We manipulate those strings, we concatenate values, we split them out, we compare values, and string handling is really quite ubiquitous to a business application. And we've done a total refactoring of the string handling. The language itself has been enhanced, eliminating round trips between the client and the server. The BBJ list control and the BBJ lost focus and BBJ edit modify and BBJ form validation events now carry client-side information, meaning that the server doesn't have to go back to the client doing round trips to query that information, greatly reducing and improving the performance of high latency GUI and of course BUI applications. We've improved the initialization of the thin client. By utilizing PAC 200, we're able to utilize jar sizes by up to 30%. In the database and file system arena, we've optimized concurrent multiple file opens and made them significantly faster in heavy load conditions with multiple users opening multiple data files at the same time. The BUI environment has been optimized with dramatic improvements on the startup of your BUI application. We've also implemented form validation for BUI, reducing the round trips required to validate various fields on a form. And we encourage you to use CSS to do client-side graphics, offloading the performance requirements from the server down to the client. So to measure the performance impact of our massive refactoring of our string handling, we created some micro benchmarks. These shouldn't be confused with real-life application examples, but merely exhibit the significant improvements to specific code samples that do string manipulation. And you'll see from this graph we have very significant improvements from BBJ 12 versus BBJ 11, probably on average around about a 50% gain in performance. If we look at the function timing comparisons again, BBJ 12 to BBJ 11, where the functions utilize strings, we see some very dramatic gains in performance. A couple of minor regressions, but on the whole, substantial performance gains across the board. If we then look at verb timing comparisons, so verbs that might utilize string assignments, for example, looping, we see performance gains in certain aspects up to 30%. So string optimizations not only improve performance, but also reduce CPU usage, and we reduce memory consumption. Garbage creation is reduced, and therefore the need for regular collection is reduced, leading to better performance. Let's utilize a Java performance monitoring tool to see how the string manipulation tests perform in BBJ 11 versus BBJ 12. So in BBJ 11 we ran these three times, once, twice, three times, and we'll see that our CPU usage is up there just below 40%, that's where it peaks. If we look at the heap, we climb all the way up on the heap size up to 1 gigabyte, and the used space, the used memory, goes up to 578 megabytes. Now let's compare that to BBJ 12's string test. So the same string test, iterated three times, hardly has any CPU usage by comparison. It's right down here below the 10% level. And very interestingly, on the memory consumption side, we're actually only up to 150 megabytes of total heap. This is versus 1 gigabyte over here with BBJ 11. And the used memory space is only 94 megabytes versus the 578. So very substantial reduction on the memory used, and the garbage that is generated. Therefore, the number of garbage collections is reduced substantially, improving the overall user experience within the JVM. Speaking about the JVM, BBJ 12 supports Java 1.7, and there are significant speed improvements. So Oracle has contributed to a faster BBJ. And as a reminder, support is ending for Java 1.6 in the fall of 2012. Let's have a look at those same string timing tests, those micro benchmarks, but this time comparing Java 7 versus Java 6. And we see we get some nice performance gains here as well. Not nearly as much as the BBJ 12 to BBJ 11 gains, but still very substantial. Again, on the function timing, some nice gains. And finally, on the verb timings, we also get an overall gain on Java 7 versus Java 6. Next, I'd like to have a look at the performance gains we achieved by reducing those round trips between the client and the server for both GUI and BUI applications. So let me hand over to Nick to take you through a demonstration of the benefits we had with the home mortgage application.
After form validation was available for BUI programs, we decided to put it to the test in various distributed environments. Our test program was the BUI mortgage demo, which was a perfect test case. It mimicked a real-world application, but due to its smaller size and reduced complexity, it was easily manageable. The BUI mortgage program, shown here, is a souped-up version of the old _mort program, shown here. Although the BUI version looks a lot different, we reuse some of the calculation code from the old _mort utility. However, the BBJ version is formatted a bit differently so that it's easier to read. There are no line numbers, if-then structures can span multiple lines, and you can even use mixed case. When running the mortgage program, the user starts off by entering the data values into the various fields, such as the principal amount, percentage down, etc. These values are required for the program to calculate the monthly payments. So after the user presses the Calculate button, the program retrieves the numerical values from the client's computer. In a distributed environment where the server and client reside on different machines, network overhead and latency determine how quickly the program can retrieve the information. Our test case used two different versions of the mortgage program. The older version that retrieves the contents of the controls by querying the controls directly, and the new version that uses form validation and retrieves the contents from the BBJ form validation event directly. Because the program gets the information from the event rather than the controls, it doesn't have to communicate with the client and avoids all of the networking overhead. Our first test compared the pre- and post-validation versions with the client in Albuquerque, New Mexico, and the server on the West Coast in California. With an average ping time of 45 milliseconds, it took 3/4 of a second to retrieve the contents of the 7 input controls using the old version of the program. In contrast, the new version, which uses form validation, retrieved the same information more than 10 times faster, bypassing the round trips to the client and retrieving all the information in only 68 milliseconds. Our second test was similar, except that this time the server was located in Ireland, approximately 4,700 miles away from the client. Ping times increased to 188 milliseconds, which were significantly higher as we expected due to the longer distance. This increased latency made form validation even more critical, and the new version of the mortgage program was now more than 20 times faster. The total time to retrieve the field values dropped from 1,796 milliseconds down to a scant 84 milliseconds. You'd think that such a big win in performance would have a cost. After all, we did have to change code in the mortgage program to take advantage of the new BUI form validation. However, we changed a lot less code than you'd think, and even the lines of code that we did modify, we didn't have to change them much. Here's a look at the differences in the two versions using the Basis IDE's diff functionality. The first change was to the process events, as the Calculate button now responds to a form validation event rather than a regular old push button event. Next, the new version has some extra code shown in green, where the program retrieves the form validation event that contains the information for all of the controls on the form. The next few diffs make up most of the changes. The program used to set variables by getting the values from the controls on the form. Now, The new version sets the variables by getting their values from the validation event, passing in the control as the key. So even though the lines have changed, the syntax is very similar. Lastly, the new version accepts the validation event, unlocking the form so that the user can change it once again. So overall, the changes were fairly limited and were pretty easy to make. And those changes were definitely worth it, as the calculation routine is now noticeably faster.
Thanks, Nick. This graph is really very telling. Even our example here with a 45 millisecond latency between our offices in Albuquerque and the server in California, we see this huge performance gain, going from over 150 milliseconds to begin with to just over 50 milliseconds. And you should see similar results in your own thin client deployment over a similar type of latency environment. Let's turn our attention to Barista runtime performance gains. Barista 11 versus Barista 12 benchmarks. In both cases, we're running on the same BBJ and the same version of Java. The only difference being that we're running a different version of the runtime for Barista. We're going to see three examples, one of the BUI and SysGUI grids, secondly Barista header and detail grid with core point code being invoked between each line, and finally a Barista query optimization. In all of these benchmarks, we're running a timer that communicates via namespace with either the BUI or the SysGUI components. This first example has three interpreters running, one the stopwatch and running SysGUI, and two versions of BUI, one 11.12 and one 12.0. Both of them are grids that we're going to load up. They are the Barista states file from the samples, the examples that ship with the product. So let's start up the 11.12 version. We'll see our stopwatch is running, and this is going to populate the grid in the BUI environment. And then we can reset the timer and then restart the 12.0 version and see how that compares. And we can see substantially better performance, more than 4 times faster, and these enhancements will also be apparent in SysGUI. Let's look at our second example, which is a header detail example, header with a detailed grid. And in this particular case, we're going to be working with a 400 row data set that's going to be populated in the detailed grid. And we're also going to have some core point code that is going to execute between each row being displayed. So we start up 11.12 version, and so it's going to populate the full grid and show the time from start to end of loading up and executing the core point code at each point. So 15.2 seconds to display that, which may not be too bad depending upon the amount of work your core point code is doing. But let's reset the clock and see what performance gains 12.0 gives us. So rerunning the same process, exactly the same code, we deliver the result in 3.4 seconds, more than a 4 times performance gain. Again, this performance most discernible when we have core point code. Our last example is an example of the optimization we've done within Barista of query definitions, optimization of our SQL. In this case, we have a 200,000 row record set that we're going to populate. And when we test this query, the time that it's going to take here to generate the result is not just the display, of course, it's gaining the result set from the SQL query, which is the bulk of the work, and then displaying the results in a grid. So it begins display around about 16, 18 seconds through, and then at 20.5 seconds we complete the display. By now optimizing with work that we've done with our engineers on the SQL side, we can regenerate that display in only 0.7 seconds. So very key that we optimize that performance. So very dramatic performance gains with Barista's runtime engine. In all three of these general use cases, 1.6 seconds to generate a BUI grid, over 4 times faster for header detail grids with core point code being invoked between lines, and lastly the Barista query optimization with a 200,000 record set, only 0.7 seconds. So if you've had any qualms about utilizing and leveraging the productivity gains from Barista, now's the time to put those aside and take us up on the challenge. Speaking about development tools, we also have in the last year released the new IDE Dialog Wizard. It's now fully supported in BBJ 12. It's an alternative to App Builder. Its key difference is it generates fully object-oriented BBJ programs from a resource file, automatically generating the callbacks and the method stubs. But, quite interestingly, it also preserves your custom editing to the resultant BBJ code, allowing you to go through a second pass or third pass to leverage any changes you made to your resource file. It also optionally generates the automatic tool button for integration to Barista. In addition, the new IDE Dialog Wizard gives you the ability to automatically test it, giving you a launcher to launch a GUI or a BUI version of your dialog. And it also outputs JavaDoc-like documentation. More about that later. Let me hand you over to Ralph Lance to take you through a demonstration of the IDE Dialog Wizard in action.
I'd like to show you just how quick it is to go from a resource to a running dialog program. Here we have a customer maintenance form. Having created the resource, I do a right-click on the resource name in the File Systems navigation tree of the IDE and choose Run Dialog Wizard. Dialog Wizard is started, gives me a suggestion of the program path of the program that is going to be generated. I can choose among the top-level window IDs to steer this session of the wizard. Choose Next, Next. I do have to react at least to the close event when the main window is closed. Next, Finished. I have a BBJ program. I do have to make one small change for this presentation, but it's already prepared for me. I just need to remove this rem to have the window centered within inside of our presentation. Now we can run it. I can choose to test in GUI. There's our dialog. I run it again and test in BUI. It's never been easier. One thing to note is there are no data files per se used by the Dialog Wizard for settings entered or chosen for program generation. The program code itself contains this data. Throughout the use of identifiable begin and end code blocks, for example, DLG Wiz, DDX begin, and the matching end block, the wizard knows where to look and parses what it needs from the program code. Any code outside of these blocks can be anything at all and will be simply taken as is in the regeneration process. One thing to note is that Barista is not required to use the Dialog Wizard and dialog programs generated by it. The Dialog Wizard strives to be a productivity tool for individual dialogues that optionally can work with Barista. Let's take a brief look at how we can use a Dialog Wizard generated class in conjunction with Barista. So we run the Dialog Wizard and skip over to the toolbar section. We have a maintenance form and we'd like to have the toolbar located at the top. Now for this demonstration, in order to show you how the interplay works between the toolbar in our dialog and the Barista MDI, I'd like to just change this to a tool button toolbar because I'd like to use the toggle function to show you the reaction between the class and Barista. So let's do a finish. It's regenerated our program, and inside of our program we have the stubs for all of the tool buttons that we see down here. So what I'd like to do is I'd like to add a little bit of code to the Options tool button within inside the toolbar. So I've prepared a little bit of code to expedite our presentation, and I'd like to add that to the code within inside the dialog class. Now please note I'm outside of any Dialog Wizard blocks, so this code will be preserved between generations from the Dialog Wizard. Now if I run this within inside of GUI, then I see the toolbar, and when I press the Options tool button, then I've instructed that the first, previous, next, and last navigation buttons should be disabled. And we see that we do that. I press it again and they're enabled. So let's take a look at this inside of Barista. Let's start up Barista. I've already prepared a menu item in order to invoke the dialog. And that's found in the examples Dialog Wizard and Customer Maintenance. This calls the form that we just generated. Here we see the form has the toolbar, and we also see a corresponding buttons in the toolbar of the MDI as well as in the menu of the MDI. So now when I press the Option button, the buttons are disabled in our dialog as well as the MDI toolbar and in the record menu of the MDI.
Thanks, Ralph. So just to recap, the new Dialog Wizard is great for rapid application development of your GUI apps, your BUI apps, and for your custom Barista code that maybe isn't well suited to the Barista data dictionary paradigm. So you can create that handcrafted code and very easily plumb it in to your Barista code. To view the extended video, which has a bit more background detail and technical information, we'd invite you to go to links.basis.com/dwizard, short for Dialog Wizard. Next, let's look at the BBJ to JavaDoc Wizard demo, wherein we show you how, with a little bit of effort on your part, we'll give you the ability to rapidly document your application code. Let me hand you back over to Ralph again to take us through that demonstration.
In order to help in the effort of documentation, Basis has created a utility called BBJ to JavaDoc. Based on the JavaDoc standard, we have modeled a way to add documentation within inside the program code, which is then parsed to create very nicely structured HTML documentation. Based on an example of a Dialog Wizard generated program where this documentation automatically resides, I'll be showing you how to use BBJ to JavaDoc to create the documentation for this program. Here we see an example of the program code with some JavaDoc standard documentation within inside of the code. The constructor is JavaDoc for each method resides within inside of the program. There are certain types of flags that JavaDoc will respond to in building the end documentation. So let's see how this works. Under utils BBJ to JavaDoc, there is a program called BBJ to JavaDoc Wizard Run, which we need to run in order to start the wizard. After the wizard is started, we have to stipulate where we'd like to have the documentation generated. We can assign to what level of scope of visibility we would like to have documented. In this case, we are going to choose private because we'd like to have everything documented. And we have to choose the BBJ source files that we'd like documented. So we'll navigate to our D Java break and choose the BBJ program to be documented. You can have a whole slew of programs and they'll be documented at once. Press Next. Here are typical JavaDoc options that can be used when the documentation is being generated. You can read about this in Internet under the JavaDoc standard. Press Next, and now we're ready to have the documentation actually generated. After the generation process, because we have the flag Show Results checked, we will then see the results of the generated documents immediately within inside of a browser. So here's the nicely structured JavaDoc for our program. We can easily navigate between the different aspects, the field summary, the constructors, or the methods themselves. If I'm pressing one of the hyperlinks for methods or for fields or the constructor, brings us into the code directly where the entity is defined. The program that is shown here on the screen is a copy of the BBJ source program and is not the program itself. So this is a great way to get structured documentation for a class or a set of classes.
So in summary, we've seen how BBJ 12 is the fastest BBJ by far. With the refactoring of the string handling, with the addition of the language verbs to accommodate fewer round trips in high latency environments, BBJ has been optimized. Java 1.7 is faster than 1.6. Barista execution is faster in the runtime environment. And our development tools, custom development is faster. The Dialog Wizard facilitates custom development to be integrated into your Barista project. And creating your documentation is faster. So let's take your questions.